Hey everyone, welcome back. Today we're going to be taking a look at Phyllotaxis in TouchDesigner, which is the process by which plants add new organs to their bodies. And in this case, an organ means anything like a petal or a seed or a new leaf. All of these arrangements follow a predictable set of rules, and they lead to these patterns that you're very familiar to seeing, whether that's like a cactus, the head of an artichoke, the petals on a sunflower, etc., etc. So we're going to take a look at implementing this in TouchDesigner, which is actually pretty straightforward. So without further ado, let's jump into things. So here's what we're looking at, but let's just take a step back for a second and kind of look at where we're going. So here is a little bit of the system that I have built, and there are some options that we'll be able to give ourselves, one of which is kind of using this growth animation, which is called zootropic animation. We'll go into what that is and kind of where it comes from. It's a really nice effect, I really like. We'll be able to kind of define exactly how big we want our Phyllotaxis to be. And one other thing that we'll be able to do is if I turn down that zootropic animation and turn up this animation, you can see that some pretty awesome designs can be achieved very easily. And this is only by changing one parameter. We will go into exactly what that parameter is and why it has this effect in a little bit, but I think this will be pretty fun. So I'm gonna turn this off for a second, and we'll leave that there. And then one of the other things that I wanted to look at before we get into rebuilding this is just how easy it is going to be for us to kind of change the color palette. And then finally, last but certainly not least, we can also grow these structures. And so you can add these effects together for a lot of pretty interesting dynamics. And so, yeah, I think this is probably a good place for us to just jump into things and start to see how you guys can build this all on your own. And so, let's do that. I'm gonna delete this, delete that. Okay. Bring our angle back to the original, and we'll talk about why that's the default number also in just a second. So I'm going to actually move this over to the side here and grab this. So this is The Algorithmic Beauty of Plants. It's the name of the book. It's very interesting. Highly recommend to skim at some point if you are feeling bored and motivated. This is where the core of the algorithm comes from. And there's a lot going on. It doesn't really matter that much for our implementation here. We're going to be implementing this just on a 2D plane. There's some extensions that we can potentially investigate in a further tutorial, but this is the simple use case, and so we're going to start here. Really, this little section is going to contain almost all of the information that we need. So in order to describe the pattern of florets or seeds in a sunflower head, there's this formula which basically takes the number of the floret, which is just going to be linearly increasing from 1 to n, where n is the total number. Phi, which is in this case the golden angle, or 137.5 degrees. And then this constant, which is going to be effectively a measure of spread, and that constant is going to help determine radially where that floret or organ is placed. So you'll see we multiply this golden angle phi by the current number of our floret or organ, and so that means that each successive one is placed a rotation kind of around the structure. And now here we have a couple examples of how using different angles can lead to different structures. So, now that we have a little bit of an understanding of kind of the basis for what's going on here, we can return to TouchDesigner and start to try and implement this ourselves. Now, I'm going to just, I think, delete about all of this. It'll be pretty straightforward to bring back. And so we can start from actual scratch, although I'll leave my palettes, and I will delete everything else, and we can start from scratch. So, first things first, we're going to drop down just a regular GLSL multi-shader. And I'm going to open up my parameters here, and I think I'll just get rid of all these so that we can recreate them as we go. And so the first thing we'll need is number of organs. That'll be an int, and I'll make that range max like 1,000, and my default, I guess, will just be 500. For those of you that don't know, this is the function store toolbar. It's open source on Dan's GitHub page. Highly recommend you go and use that for quality of life in TouchDesigner's development. There is very little that I find as helpful as this. But anyway, let's take our number of organs. We're going to drop them on the X dimension of our GLSL shader resolution and then make the Y dimension 1. So now we have a nice little row of pixels. And we can actually just use this to kind of create our phyllotaxis patterns. So I'm going to edit my shader. I'll bring this over here and move TouchDesigner over to the side. And then I'm going to, oops, that's not right, view the contents of my GLSL info just down here, so we have it as a floating window, which will make it a little bit nicer for development. So now we have our shader. I think actually I'm also going to try and keep this up. Just like that. And so sorry about that. And so now we can kind of move forward. And so our goal is going to be to implement this little bit right here into a GLSL shader where we're treating each pixel as a floret, and we're going to try and arrange those florets by following the instructions laid out here in Vogel's formula. So, Taxis shader, and we'll say based on Vogel's formula from the algorithmic beauty of plants. And then I'm just going to copy this and put it here, so that way we're nicely attributed. Okay, so to keep things very simple, first we're just going to try and output our position. And so I'm just going to update this. I know we're going to need more buffers eventually, so I'm going to just type layout location equals 0 out vec4, and then I'm going to call this O position, and we'll just update that frag color to opos. And so now we have a out position buffer that's going to take our outputted position. Now we don't need to read in anything at the moment, and so we really just need to try and figure out a way to implement this formula. To do that, we'll need a couple of things. We will need the concept of n, and n is going to be our pixel number. And so we can say int n equals int gl fragchord.x. So this will be number of pixel or floret. We'll also need the total number of florets, and so for that we can actually just use our dimension. So we can have int big N, and this will be int, and we can use an inbuilt uniform utd output info.res.z, and that's the x resolution of the output color buffer. And so now we have all the petals, e.g. total number of florets. Okay, we're going to need some concept of spread, and so for that I think I'm actually going to use a uniform. Whoops, not that. Uniform float, and I'll call it uSpread. uSpread, and I'll just set this equal to like 2 right now. And then finally, we'll also need an angle. And so for this, I will also have an angle that I'll define, and I'll make that 137.5 right now. And that again is just being taken right from the paper here, 137.5 degrees, which will be our phi. Okay, so a couple other things that we'll need. So to determine the actual rotation for any specific floret, we're going to take this information and we're going to basically use it for positioning each of our florets. So let's have a center, and I'll call this vec2 center and just set that equal to 0. Then we're going to need a radius, and this radius, using this information in the paper here, is going to be equal to our spread, which I guess I'll make a variable and set it equal to uSpread, so then we can use this variable here, times the square root of n. And this n is small n, which is the number of our specific pixel. So this means is that as n increases, the radius is going to be increasing. Then we need the angle that will rotate this specific floret by. We'll call that phi in this case. And this will be our angle, which will be u angle times, and in this case, we need to convert it to radians. So I'm going to say pi over 180, but we don't actually have this pi right now. And so we need to define it. So I'm going to say up here, define pi as 3.1415926, which is about as much as I remember, but should be good enough for our purposes right now. And then we have our angle in radians. And then finally, we need the actual angle that we're going to rotate the specific floret by, which is going to be called theta, and that will be our phi times our n. Angle of rotation for specific floret. Very good. So now we just need to apply these values to our center. So we'll say vec2 xy, and then we're going to create a vec2, which will have r times cosine of theta plus center.x, sorry about that, plus center.x, which is not quite right. And then for the second component, which I'll put over here, r times sine of theta plus center.y. Now we're doing this on a two-dimensional plane, but we might want to have like a little bit of z-space movement just for nicer rendering. So I'm going to define z, and I'm just going to have this be basically the number of the floret times some small multiple, so that our Z will change slowly as we have more florets added. And then finally, I'm going to define, well, actually I'm just going to output the R. And so here we will have color equals vec4, x, y, z, and then R. And so now if we go back to our TouchDesigner, take a look, drop down the null, we can open up the viewer here and press V to view this as points. And okay, something is a little bit off. Our shader should definitely be a 32-bit float shader. And now if we view this as points and press H to home it, we can see that indeed we're starting to get this phyllotaxic pattern, which is exactly what we want. And if I go back to my shader and I add a spread uniform, which will be a float and can go from 0 to 4 with a default of 2, and then an angle, which can go from 0 to 360 with a default of 137.5. So we use that angle, drag and drop it on there. We'll use that spread, drag and drop it on there. And so now, before we even have any rendering, we can see that as we change this angle, we get some really cool patterns. And that's a function of nothing besides the fact that this angle is essentially rotating each successive point. And so you kind of have this like compounding rotation effect, which leads to these patterns that form as you choose different angles. And so different angles will have substantially different properties. This 90 looks very close to just a cross, but just 91, you have some really cool spiral shapes. And then obviously 137.5 is our pure phyllotaxic layout. Now, that is honestly the core of the algorithm. Everything that we're going to be doing from here on out is going to be kind of rendering and making things look a little bit nicer and adding some animation. So before we move forward, I'm going to define this Phyllotaxis as a function. And so for this, we'll take in int n, we'll take in an angle, we'll take in a size, and we'll take in a spread. And we'll basically do a lot of this stuff. I can move this n declaration actually out of my function main and call it const. And that way we'll be able to kind of use that. Actually, it doesn't need to be a const, it can just be an int. We'll be able to use this big N in all of our shader code, which is great. And then I'm basically going to take all of this stuff, move it up into my new function. Instead of setting the color to this, I will return it so that we output a vec4. And what else do we need? So this phi should be using our angle argument instead of our u angle. This spread should be using our spread instead of, well, I guess we actually just don't even need this line at all because we have our spread coming in here. And then say vec4 equals Phyllotaxis, and then here we have n. We can have our u angle, float size. That can be, well, we're actually not even really using that at the moment, which I think is actually fine. We can use spread and use size later. So we actually just need n, angle, and spread. And so we can use spread here. And this is just going to be to refactor out our calculation a little bit so that we can then just have some nice looking code and things will make a little bit more sense. when we move forward to doing more interesting things like animating them and coloring them. So now we have our Phyllotaxis as a function and some nice clean code. We don't really need this planar model anymore, so I'm going to just get rid of that. John Gerd, he's great. Yeah, and so that's the basics. So I think actually before we go forward on doing some more stuff on the shader side of things, we can just render this really quickly. And so first I'm going to get a sphere. I will use a transform, and then actually in the middle there I will also hit an attribute create, because we're going to do some PBR rendering after this. Then we'll middle mouse, we'll drop down a geo, we'll get a render comp. I'm just going to use, well, actually, I will use the palette, Control B to open that, camera viewport, and then drag and drop that onto my camera parameter on the render top. And then in this case, I'm just going to use a normal light for the moment, which I will parent to the camera. And now we can rename this null1 as pose, just like that. And then I will go to my geo, I will turn on instancing, I will translate op with my new pose null, and then we'll use R, G, and B to translate that texture. Alt-N to drop a null after the render. Before we go anywhere, I will use the render parameters by dragging and dropping them onto my parent. And that way, we can now set these to be whatever you want. I'm going to set mine to 4K, but do whatever is right for your computer setup. Okay, so we're a little bit kind of zoomed in. We can just use this camera viewport and hit home all, and that's going to nicely zoom out for us, which is great. And so now we can see, especially if we use this number of organs, that as we add organs, they are all being added and grown, just like we were expecting. Changing the spread, we can see they go, closer together or more spread out. And then changing the angle, of course, we get all of our really cool designs. Awesome. So now we have that set up. One thing that I do like to do is maybe just use something that's not quite a perfect sphere. So this just kind of like oblong shape. Once we add a little bit of rotation, it'll look more interesting with this oblong shape. Okay, so now we have kind of a render set up, and I think maybe I'll just zoom the camera out a little bit more so that we can see all of our picture. And actually, instead of 4K, I'll just make it 2160 by 2160 and zoom the camera back in a little bit so that we can have this open on one side while our code is open on the other. And I'll zoom this in just a little bit. Apologies if the beginning code was kind of hard to see, but here it is again. Of course, this will all be available on my Patreon afterwards for anybody who's interested. All right, we'll view this in our text port again. Okay, so now what do I want to do? Now I want to basically just refine this and make it a little bit more interesting, nice to play with, and, just like a little bit more artistic. So the first thing that I want to do is have some semblance of kind of dispersion as we move further out, right? So I want my stuff in the middle to be a little bit smaller, and then also kind of packed closer together. And I want my stuff further out to be bigger and spread out a little bit more. So one thing that I'm going to do at this point is start using additional color buffers to deal with this information. So I'm going to give myself like 4 color buffers. And if you guys aren't familiar with color buffers, it's essentially just a way to output more textures in GLSL shader. We can use a render select, drop it down, drop our shader on top of it, and then this index is going to allow us to choose different color buffers from our shader, which we can define using this layout, location equals 0. So in this case, what we're really saying is our location equals 0 color buffer, or the first color buffer in our output array, is going to be called oppose, and is going to hold whatever data we assign to oppose in our shader. Then successive outputs, which, for example, we can have another one. We can increase the location to 1 and call it O scale. And so now, if we change this render select to 1, well, there's no data right now, but if we went down here and we said O scale equals TD output swizzle vec4, just output 1 for now, then we'll see we have that output here. So I will call this rotation out. And just for good order, we can take this rotation out, we can rename it to pose out, and use index 0, and then use that for our actual position output, just to keep things nice and orderly. And then I will use a null after this rotation out, and I'll call that sorry, not rotation. This is scale. Scale out, scale. And then we can use that scale on our scale up. Right now the scale's just 1, but maybe we want to do something interesting. We can say something like float size. And then we can make this size also maybe a function of actually the number of the floret, since that's what we've been using for a lot of these other things. So maybe first we'll just say n over n, and we will output just size uniformly across all dimensions of our scale vector. Now this is probably going to, oh, there is no n, this needs to be below us defining the n. And so now we can see our scale, if we hit n to normalize, is going to be 0. I think that's because we're dividing, and it should be a float division, not integer division. And so now, as expected, our size is going to go from basically 0 to 1 over the course of these radial layers. Which is great, but I don't want my size to be like 0 in the middle, so I'm going to say 1 plus this number, so that we start with 1, or like, you know, kind of the smallest size in the middle, and then that size increases as we move outward. Increase size as we move outward radially. Okay. Now the other thing that I'd like to do is change the spread, because I would like my units to be closer together when they're smaller and further away from each other when they're bigger. So we can make something called spread here, and in this case I think that I want my spread to actually be like mapped from one range to another. So let's just try first. We'll say spread equals size, and we'll see how that looks. Maybe the spread can just be this part without the 1 plus. Ah, we're not using spread, we need to use it instead of use spread. And there, okay. So now we can see that if our spread is basically just our size, maybe -1, that we already kind of have this effect, which is great. And as we increase, well, our spread doesn't do anything right now, I guess. So we want to still be able to increase and decrease this spread, but kind of retain this dynamic spacing. So we can have a map function that will help us do that. We can define float map, float x, float a, float b, float c, float d, and then we can return c plus x minus a over b minus a times d minus c. And so that's going to take in an input x on the range a to b and map it to the range c to d. So now we can make our spread something like map. We can map the actual instance number from 0 to the total numbers, and we can remap that to the range, let's say, I don't know, 0, and use spread. So now as our spread increases, we are okay increasing that, great. But maybe we don't want it to be quite 0. There should be a little bit of spread, so maybe we'll start it at like 0.5. And I think that is, yeah, starting to look a little bit nicer. Which is great. I love that density kind of there at the beginning, which I think is wonderful. All right, so now let's add some rotation. And for this, I'm going to do another color buffer. This one will be called O-rot. We'll have a vec4, which we'll call rotation. And we're actually just going to make it vec4. We're going to take the RGB values from our Phyllotaxis output, which maybe I should name as pose instead of phi, just to make it easier. And then we can just use 0 for right now. Okay, we'll update that in a second. The other thing that I want to add at this point is the zootropic rotation. And so one thing that, let's see if I can find this. Zootropic rotation, Phyllotaxis, animation. I should have had this ready. Sorry, I'm trying to find a specific website that had a really good example of this. Maybe this will work. Oh, well, John Edmark is great. Definitely want to look into his work. Okay, well, I can't really find it, I guess. But basically, the way that the growth effect that I showed you earlier at the beginning is actually achieved is not by actually moving any of the actual instances as you would think. It's actually by just rotating the entire thing every frame, and it's essentially an optical illusion that results in the effect of kind of a continuous rotation and growth, but it's really just us rotating the frame or rotating all the positions by quite a lot each frame. So I'm going to define phi up here as 137.5 because that is our phi angle, and the reason for that is because we're going to want to rotate by this angle regardless of what our actual angle is for placing the organs. Now we will need a 3D rotation function, so you can just Google rotate Z GLSL, and there's a lot of different options here. This is one that I've used before. There's also a lot of other ways you can do this, but I think this is just easy in case you don't know the actual math. You can just copy and paste this function right there, rotation 3DZ. And this is returns a matrix, so we actually multiply our position by this matrix to rotate it. We'll say pose.rgb equals pose.rgb times, and in this case we'll use our rotation 3dz, and then in here we're going to use phi times pi over 180, which is going to convert it to radians, and then we're going to multiply this by a uniform that we need to put in called uframe. And uframe, there we go. We'll add that to our vectors. And then I'm actually going to drop down a speed. I'm going to insert a math. This is, by the way, the just function store presets that allow you to drop down some templates. If you don't have that, you can just use a constant and a math and a speed, and that will get you to exactly the same place. This math is going to be multiplied by 10. Then after the speed, we're going to put a limit, and the reason that we're going to put this limit is to quantize by rounding down or flooring to the nearest integer. And then we'll just drop a null after that for best practices. And then this is going to actually be our frame. And we can see that once we have this frame updating every frame, then this is being rotated by an iteration of the golden angle, or phi. And so we can kind of see this growth happening now, which is, well, exactly what we were looking for. And so we can also obviously increase the speed to, you know, higher values, which has this growth happening faster. And that's great. I really like this dynamic, and we can zoom in on our camera a little bit. And yeah, that growth is really nice. I like it a lot. You can also see that we do actually have some z space here because of our z term in our function, which is great. Okay, so now we're really getting there. This is a long way towards what we're trying to do. We can bring in our rotation by rotating to our rotate op and using RGB for those rotations, and we'll, whoops, that doesn't actually matter. We need to output this. And there we go. So now we have nice rotations that are kind of pointing in towards the center, which really leads to our plant look, which is great. So now we have the rotation, we have the ability to change the spread, we have the ability to change this angle and really make it do a lot. I think I will drag and drop this speed parameter and maybe give it a range of like 5 or something. And one thing that we do probably want to do is like loop this in some value that's maybe, I don't know, 2000. As those values get a little high, there are some rounding errors because we're basically quantizing at one point in our function, and we're using imprecise values for pi and other things. So It gets a little bit jittery if this phi multiplication scalar, i.e. U frame, is super high, which shouldn't really be a problem. So I'm going to turn off that rotation for now. And maybe I'll just update this parameter to be called zootropic speed. Great. So now let's look at coloring, because that is one of the main other pieces. So I'm going to keep this palette. I'm just going to wire it right into my GLSL. And I guess I should have changed my resolution to custom before I did that. I'm going to define an input. And then our color, in this case, is going to be... what is it going to be? It is going to be texture, STD 2D inputs, and here we'll use the palette macro, and then we're just going to grab vuv.st, because again, that's going to be based on the pixel location, and in this case, we have just one of our pixels, so it's basically going to sample a different pixel from our ramp for each of the iterations. We can use a color buffer one more time. This will be our last one. Color. It's really pretty easy once you kind of understand how these things work, and then you can have a lot of powerful code that you're writing with multiple color buffers. So now we're outputting a color buffer for our actual color. This will be index 3. You can see that color here. We'll call this color. I will call this color out, just to keep things really nice and tight. Go over to our geo, go to the color 2 tab, go to this color op, RGBA, and now we're starting to have some coloration on our petals or florets. Now, maybe you want to have an easing curve for that color lookup, so I'm just going to drop an S curve down, add a null after it, go back to our GLSL. On the array tab, you can drag and drop that null, which I guess I'll rename as color easing, as the chop, make it a texture buffer, name it S color curve. Go back to my shader. I will define it as a uniform sampler buffer S color curve. And then instead of just using this lookup as a vuv.st, we can say vec2 lookup equals vec2. And then here, we want our x component to actually be grabbed from that easing. And so with that, we can do texel fetch S color curve, and in this case we just want to use our n.r, and we'll need to move this n up above this so that we have access to it. And then this should be a comma, and then we just want 0 for the y value of our lookup, and then we can use this lookup so this is going to grab the actual sample of this curve. So this curve should be a length equal to our number of organs. And that's going to return a value. We'll return a lookup value from 0 to 1 based on easing curve. And so then that's the value that we want to look at in our palette sampling. make this 0.5 because we actually want to sample it in the middle of the pixel as far as the Y dimension goes. So now we have this color lookup that we can control based on this easing curve, which is great. And what else do we need to do? I think the last piece that I want to do before I leave it is just add a nicer PBR rendering term here. So to do that, well, actually, before I do that, let's do the last thing that I want to do in the shader, and that is if I zoom out and turn on zootactic speed, we can see that our things are kind of like disappearing up here in a way that I don't like. It looks a little bit like choppy to me. So what I would like to do is use something to kind of be able to smooth that out a little bit. And so to do that, the last piece that I'm going to try and add to this code is a fall-off curve for our scale. And we can probably use it for the color too. So we can use, I think, another float. I'm just going to call this falloff. And this is going to be equal to let's say smooth step between 0 and 1, and this will be 1 minus n over big N. And so that's going to be little n over big N is from 0 to 1, so this is basically going from 1 to 0. And then if we take this fall off and multiply, well, first we'll set color.a equals fall off. And then we can also have our size times equals fall off. Oops. Okay, so this isn't doing a ton at the moment, and that's because, well, you can see like a little bit, but not very much. What we probably also need to do is have some sort of an edge so that we can define exactly where this is occurring. I'm going to add 2 more uniforms to my vector page. This is going to be called uEdge, and this is going to be called uSoftness. I'll set this at 0.1 for the moment, this at 0.1. And the reason that we want to do this is because we don't want to smooth step from 0 to 1, because that results in kind of the entire thing being like a weird easing function. And so what we really want to do is try and have it be like 0 at the very beginning, then 1 for most of it, and then 0 at the very end. Okay? And so for that, I'm going to set fall off equal to actually smooth step uEdge minus uSoftness, and then this is going to be uEdge plus uSoftness. Oh, whoops, I forgot to, so I'm gonna undo that change. I forgot to add those vectors here as uniforms, so I will do that. And then, so now we can see, okay, not, okay, there. So there's like a little bit happening, but not too much. Doesn't seem quite like this is working the way that I want it to. Oh, I understand. I see what's happening. It's again because this. Okay, so I actually probably I should use this part. So I think the issue here is because my 1 minus n over n should have been wrapped in some floats, because we want that to be a continuous valued function. Okay, so okay, so the problem here is that this needs to be using the ends cast as floats. So we'll just do that, and it's kind of annoying, but there we go. And so now we can change this edge and the softness and kind of control how the fall off is going to work on our rendering. And then if you want it to be a little bit more severe, you can just kind of add multiple iterations of this fall off, and because it's between 0 and 1 already, these are just going to make the curves a little bit steeper. And so there we have it. I think that's a pretty good place to kind of stop our actual rendering, or sorry, our actual shader coding. Wrap this, we'll call this Phyllotaxis shader. And so now the last thing I want to do is put a PBR material on this. So I'm going to drag and drop a PBR. I'm going to use some textures, which I will give to everybody. So first, this is going to be a environment map that I've downloaded. This will be included in the project file. We'll need an environment light for our PBR. We'll use this as the environment map. And go ahead and turn that dimmer up to like 2. Already starting to kind of be interesting. And then I have a couple textures that I'm going to use for our PBR, which I will also include in the file. And so we can just grab our PBR here. We can go to the maps. We can use this as the roughness. This will be our ambient occlusion map. And then this will be our base color map. Starting to look pretty good. We can take the camera, we can zoom it in a little bit, and then we can go to the PBR, we can take the metallic, actually take the roughness down a little bit, keep the metallic pretty high, maybe not fully 1 though, and kind of dial in things. Just add a transform at the very end here. Comp over our background color. And just like that. Why isn't that working? Oh, it is working. It's growing. Okay, so our Phyllotaxis is growing just like that. And I think the only thing to kind of recreate, oops, I guess we'll need to give it an out. The component that you'll need to recreate what I was doing at the beginning, which will also be in the project file, but you know, whatever. An LFO, that's a ramp, and this amplitude is going to be our number of organs. Or actually, I guess it shouldn't be assigned to that because we're about to change that, so let's just say 1,000. And then we're going to drag and drop this on our number of organs, and this is going to be our growth, and then you can change this frequency to something smaller. You can see it grow very nicely. And then also similarly, you just take like a speed. Oops. So we'll do like a constant and a speed and a null. And we can add this to our angle. Plus 137.5. And so now as we turn the speed up, our angle is rotating as we're growing and adding florets. You can turn this off and look at just the rotation. If you stop this, it will simply stop at the current angle, and we turn off this speed. Now it's completely flat. And then a reset will break everything because of the number of organs, but if we just turn this on, then we can reset and watch it grow. So, I'm going to leave things here for today. Thank you for following along. Thank you for all of the support. It obviously is not insignificant for some of you, and it's really important and meaningful to me that the support is granted. I hope that you guys enjoy these tutorials and get something out of it. Until next time, see you later.